Hello everyone, welcome to my video series on hidden Markov models. So let's start this series with the theory example and the three problems of hidden Markov model. And I hope that if you follow along this series, you're going to learn everything that you need to know about the hidden Markov models. So let's dive in. So first of all, let's look at a very simple data set. This is called the iris data set. So in the iris data set, you have the sepal length, sepal width, petal length, and petal width of different flowers. And you sort of have to predict what flower that particular sample is. So if you're given these four different values, these four different features, you need to be able to predict basically that the flower is iris sedosa. And the same thing can be said about the other samples as well. For example, the second sample, here you can see that there are four different features. You have to predict that the flower is from iris versicolor class, right? So this is a very typical kind of data set that people use in machine learning. But there is one issue here. There is one thing that you need to pay attention here is that each row here is actually independent from the other rows, right? For example, row 1 doesn't depend on row 3. So the species Iris sedosa, the prediction of that doesn't really depend on the prediction of Iris virginissa. And similarly, the prediction of Iris virginissa doesn't really depend on Iris sedosa, right? That means this particular task is not really sequential, right? But on the contrary, let's look at this task. So this is just a simple sentence. This is a book. So if you want to predict what should be there right here, so if you maybe put a gap right here, then maybe you can actually infer that this is some kind of book or some kind of noun that should sit right here based on what is coming previously. Similarly, same thing can be said for is. So if you have these right here, you can actually sort of understand that there should be some auxiliary verb like is right here, right? So these are different time steps, T1, T2, T3, T4, right? And this is a sequence. So these are the types of problems that we are going to deal with in Markov model. Another example you can see here is about the DNA sequence. So a DNA sequence is nothing but a string of A, T, C, and G. So those are the four bases in the DNA sequence. So you can think of those particular A, T, C, and G bases to have some sort of dependency on what actually came previously. For example, if you want to predict what should be here, maybe you should look at AAC, like what actually came before. And same thing can be said about G, T, and other things here as well. And there are 7 time steps being shown right here in this example. So this is also an example of a sequence where you need to actually take into account what came previously in order to answer what should come afterwards, right? Okay, so these are sort of discrete examples. Like we can literally say that this is T1, this is at T2, this is at T3, and so on and so forth. But let's look at a continuous example as well. So this is an example which shows the continuous case. So this is basically this house, and you have this nice robot which is trying to clean the house automatically. Now, in order to clean the house, the robot needs to traverse through different floors of the, whole house, right? Now, obviously, this whole space is continuous, right? You cannot actually discretize them. It's a continuous space to which the robot has to walk through. But in hidden Markov model or Markov model in general, we have to discretize our space. So here you can see that the entire house has been divided up into equal size grids. So each grid is sort of, you can think of it as T1, T2, T3, those kind of things. Like each grid is one discrete state, one discrete place, right? So basically, for example, the robot may have walked to this state at T1 at this place, then at T2 it worked here, at T3 it worked here, and so on and so forth. So T5, T4, T5, T6, T7, T8. So there are a couple of things you need to understand here. First of all, the state space is discretized, so we know which states we can actually go to. It's not really continuous here. And number 2 is the times at which we actually measure where this particular robot is. Those times are also discrete. So you can think of it like this. So after every 1 second, maybe we can actually measure the location of the robot, right? So that will be basically T1. T1 is second number 1, T2 is second number 2, T3 is second number 3, and so on and so forth. So the last thing that you need to really pay attention here is we cannot actually go anywhere. So we cannot say that the robot is here and then suddenly in time t2 it will go here. You cannot say that because obviously these things are not connected. So we have to know from which state we can go to which state, right? And how probable that is. How likely is the robot in going from this state to this state, and again from this state to this state and this state, and so on and so forth. So those are the important takeaways from this particular picture. So now let's actually look at a concrete example with numbers. So suppose we are actually looking at cancer stage. So you know that we have early stage, mid stage, and late stage cancer patients. So let's assume that we're starting from early stage. So staying at early stage is basically of zero point 0.2 probability, 20% probability. But before that, let's also talk about one thing. Suppose the discrete time steps are actually every month. So we measure the state of the patient every month, right? So in month one, maybe the patient had early stage cancer. If the patient has early stage cancer in month one, it is 20% probable that in month two, it will also have early stage cancer. But it is also 20% probable that the patient has transitioned to late stage, and it is 60% probable that the patient will actually transition into mid stage after 1 month of like looking at the condition of the patient, right? So, okay, so the same thing can be said about this plot. You can see that if we actually start from the mid stage and we measure the patient condition in the next month, it is 30% probable that it is going to go to the early stage, and it is 70% probable that it will go to the late stage. That means a patient that starts from mid stage cannot actually return to mid stage, right? According to this graph, basically. I mean, it's not reality, it's just an example. So just assume that this is the case. Then finally, you have this plot. So in this plot, we are saying that the patient has started at late stage, and with 50% probability, it is going to early stage, and with 50% probability, it is returning back to late stage when we take measurements in the next month, right? And it's never really going from late to mid stage, according to our observations. So we can actually summarize all these three into this one single graph, and all the transition probabilities are being shown right here. So you can think of it like this. Maybe the patient has started in early stage, then maybe in the next month it has shifted to mid stage, then in the next month maybe it has shifted to late stage, then in the next month maybe it has remained in late stage. So you can keep on doing this simulation according to these probability values that are assigned for each transition. So then we actually go to the idea of transition matrix. So in the transition matrix, you can see all the states are here. There are three states, Q1, Q2, Q3, and the set of states is known as a Q. So this is called transition matrix. So Aij, suppose A12. What is A12? So 1 is the early and 2 is the mid. A12 means what is the probability of transitioning from early to mid stage, right? A12 is for transitioning from early to mid stage. A13 means transitioning from early to late stage. So the probability of each row sums up to 1, obviously, because from early stage you can obviously go to only one of these three stages. There is no other alternatives, right? So that is the thing. Okay. So finally, the other thing that we need to mention is the initial probabilities. So what is the initial probability? So for example, if we actually do a random walk, if we start from maybe mid stage and keep following these arrows, I mean, maybe do some coin toss. We do some coin toss and we simulate the whole thing. We keep walking through these arrows and we count. We basically count how many times we get the mid stage, how many times we get early stage, how many times we get late stage. If we record those counts, then we can actually get some probabilities at the very end, right? So let's assume one thing. Let's assume that we have actually made transitions according to coin toss and given probability maybe 1 million times, right? If we make these transitions 1 million times and we say we get that out of 1 million times, 50% of the time, we always stay at the late stage, right? In that case, late stage initial probability will be 50%. So in this case, it is 43.6%. And then we have the mid stage, and for mid stage is 21.2%. So it's not that probable for the patient to stay at mid stage. And then finally, for the early stage, we carry it as 35.2%. So these are all called initial probabilities and they are called pi I. So pi 1 is the probability of staying in the early stage, right? That is the thing. So far, what we have discussed is Markov chain, which is basically completely observable. So everything is observable right here. We know when the patient is in early stage, when the patient is in mid stage, and when the patient is in late stage. But there is another form Markov model, which is called hidden Markov model. We are going to talk about that soon. But before that, let's clarify one more concept. So let's actually see this example. Suppose, I mean, this is just just a very, how should I say, crude example and toy example. You can think of it in that way. So suppose in month one, patient was in late stage. In month two, patient was again in late stage. Month three, mid stage. Month four, early stage. Month five, mid stage, and finally month six, it has again come back to early stage. Just suppose, assume that a patient came in and you did those testing throughout the 6 months and you get these outcomes, right? Now you may think that, okay, we have this early stage right here. So what is the dependency here? Like, does early stage depend on all the previous stages? So the answer here is no. The early stage doesn't depend on all the previous stages. The early stage only depends on the immediate previous state. So the early stage only depends on the previous state, which is the mid stage. Now, this is counterintuitive. You can think of it like it's not realistic, right? But that is the assumption that hidden Markov model actually makes. So hidden Markov model makes this assumption that any state only depends on the immediate previous state. This is a very simplified assumption, and sometimes it may not hold in real life as well, but it is what it is. That is what the Markov model actually makes assumption of. So if we want to look at this more clearly, so obviously late is Q3, mid is Q2, and early is Q1. So look, we are just naming states here. So this is Q3, Q3, Q2, Q1, Q2, and Q1. And we have pi 3 means the probability of staying at state Q3. We saw this before, the initial probability. And then these are the transition probabilities, right? So the probability of actually seeing this, the probability of getting these states is the following. It is basically this. So probability of Q3, probability of going to Q3 given that we come from Q3, probability of going to Q2 given that we come from Q3, and so on and so forth. So you can clearly see that probability of some state Q1 only depends on the previous stage, which is Q2. I shouldn't say stage, I should say state, but I mean in this example, it's stage basically. So as I said before, any state, suppose, I mean here we are talking about going to Q1, and if we want to actually measure that probability of going to Q1, we need to only consider what is previously, so which is Q2. So if we replace these things by the actual notations, then this is what it will look like, and we can multiply these things and get our probability estimate. So okay, so that is all about the Markov model, but there is some catches here. First of all, in the example that I showed you, I was talking about observing the stage of the patient, but there is basically no instrument which actually says that this patient is in stage 1 or stage 2 or maybe early stage, mid stage or late stage. And machines don't really say that. Machines give you some measurements through which you can infer which stage the patient is in. So in these 6 months, so month 1, month 2 up to month 6, people will actually measure some metrics, and one of those metrics is ctDNA level, which is circulating tumor DNA level. So normally if a tumor DNA level is high, the patient is facing a worse situation, but it's not always the case. There are some probabilities involved. So suppose in the 6 time steps, we observe that in the first month there was high ctDNA level, in the second month there was moderate, third month also moderate, fourth month low, then the next consecutive months the ctDNA level is also low. So these are called observations. So these are the things that we actually observe in the medical context or in real life context. But the stage, the cancer stage, these are hidden states. So we don't know them. We don't know them, we have to infer them. Now, there are two things at play here. Number one is the probability of observing these observations that we just saw, and the probability of transitioning from one stage to another or from one state to another. Same thing for this example, right? So combining those things, we have to sort of try to infer what are S1, S2, S3, and those kind of things, right? So if we just formalize it mathematically, so we have these 3 hidden states here, early, mid, and late stage. These are called N. These are the hidden states that we have here that we have to sort of infer. Then we have the observations basically. We have 3 types of observations: low, moderate, and high ctDNA level. We have the transition matrix A, which looks like this. You saw this before. Then we also have the initial probabilities, which you also saw before, but we have an extra thing here. We have this emission matrix B. So what does that mean? So what does 0.6 means? 0.6 means is that there is 60% probability of observing a low ctDNA level given that the patient is in early stage. Let's take another example. Let's look at point 2. So point 2 means there is a probability of 20% of seeing high ctDNA level when the patient is in mid stage, right? So you can clearly understand that when the patient is in early stage, it will obviously see one of these three. One of these three, obviously the doctor has to observe. So the probability sum of these is actually 1, right? It happens to each row. So that is basically the hidden Markov model mathematics. And we have these two things here. So the HMM, the hidden Markov model itself, consists of these five things: A, N, M, A, B, and pi. And then there is the HMM model. So HMM model is represented by lambda. And there are three things here: A, B, and pi, because these are probabilities basically. A, B, and pi are the actual probabilities, and this basically constitutes our model, because in our model we have to store these things in order to make inference, evaluate something, and so on and so forth. So let's look at this again, and let's look at how we can calculate the probability, right? So obviously we are not going to know the cancer stage. This we have to infer, but suppose in an ideal world we know the cancer stages as well, and we know the ctDNA levels, right? We know both the hidden states and the observations. Then what is the probability? What is the probability of seeing that? So we can actually represent the whole system like this. So we have first of all Q3 right here. Then in Q3 we observe V3. And so we have actually this first row, which is Q3 to Q3 to Q2 to Q1 to Q2 to Q1. You saw this before in the Markov simulation. But there is one additional thing here. We have V3, V2, this kind of thing. So these are the emission probabilities. These are the emission probabilities. What does B32 mean? B32 means is the probability of observing V2 given that we are in state Q3, right? So those are something we need to add right here as well. So how do we calculate the whole thing? This is the process. So first of all, we get pi 3, then we multiply by the observation, the belief, basically the probability of observation, then a 3-3 transition matrix. We again go here, we multiply by B32, the belief or the observed probability or the emission probability, and then we multiply by A32, the transition probability. So again, this is very important. Three things here. Number one, we have to start from the initial probability. Number two, then we have to continue on multiplying two things: the observation probability or the emission probability and the transition probability. Again, observation probability and transition probability. So if we keep multiplying those things together, we are going to get our probability value for this whole system. So in hidden Markov model, there are three kinds of problem. The first one is the evaluation problem. So what is that? So suppose that you actually observed high, moderate, low, and low ctDNA level. And you have an HMM model. So HMM model, we already told you before, it consists of three things: the transition matrix, the emission matrix, and the initial probabilities of the states, right? So if you know those things, what is the probability of seeing these observations, right? That is basically the evaluation problem. And formally it is known as probability of O, that is observations given lambda, which is the HMM model. The second one is the decoding problem. So this is, I think, the most interesting one. I find this the most interesting. So obviously you don't know the hidden states. You don't know that, right? So this I think you can all agree with me that you don't know what are the hidden states. That means for this problem, for this example, you really don't know what are the cancer stages. So the question is, what are the most likely sequence of hidden states given our observed sequence of events and the HMM model? So for example, if we have seen high, moderate, low, and low ctDNA level in the 6 consecutive time steps, which are the 6 consecutive months, then, what are the states? What are the states S1, S2, and S6 up to S6 that actually maximizes the likelihood of seeing the observations? So mathematically, it looks something like this: probability of Q, that means probability of the hidden states, given our observations and our model. So what is the Q that maximizes it? So just in layman's term, what should be the states, what should be the sequence of states that maximizes the observations that we observed, given that we have some model and obviously the observations are there. So you have to actually find those Qs, and those Qs are going to be your hidden states, right? Hidden states. And maybe those Qs are I mean, what you saw in the previous slide, late, mid, or something. I mean, the sequence that you saw, right? That is what we would expect the decoding problem to actually give us, right? So we infer the hidden states right here. So the next one is the training problem, and this is the last one, and this is also the most difficult one. And I'm going to explain this in the next tutorials. All these three, I'm going to cover all these three, and the link will be there in the description. So this is something like this. So given a set of observation sequences, so this high mod mod low low, this is one observation sequence. And you can have many observation sequences like this for many patients in the hospital, right? So O1 is for patient number 1, the observation sequence for patient number 1. O2 is the observation sequence for patient number 2. And OM is the observation sequence for patient number M. So we have this set of observations, O1, O2 to OM, and each observation sequence, for example, let's say observation sequence number M, consists of multiple observations throughout the different time steps, or in this case, throughout the different months, right? So maybe OM, I mean O1M, O2M up to OTMM is the observation sequence for patient number M, right? Similarly, we can have one for patient number 1, another one for patient number 2, and so on and so forth. So the task here is we have to find out lambda, we have to find out the model parameters A, B, and pi, such that the probability of or the likelihood of seeing these observations that I am actually showing you here gets maximized, right? That's why you have the argmax lambda. So for which lambda, for which model parameters can we maximize the probability of observing these observation sequences, right? These sequences of observation sets, basically. So, I mean, this is a difficult problem, not that easy, but I will try to make this clear for you as well. Now, one thing I want to mention here, one last thing is, you don't need to have a set of observation sequences. Even if you have only one single observation sequence, still it's enough to actually infer the parameters of a Markov model. That is what I want to mention here. So this depends on scenario. I mean, sometimes what people try to do is people try to apply the training process sample by sample. So for when each sample comes in, people want to sort of train their hidden Markov model on that sequence only, and then try to understand what are the different states and other things, right? Sometimes that can be done. But for some problems, if you have like a data set, which in most problems you should have, then you should use all of them to actually get the lambda, which maximizes those sequences. I mean, observing those sequences basically. Yeah. So, okay. So hopefully I'll see you in the next video where I will describe the evaluation problem and the algorithm to solve it in detail. So make sure to like and subscribe the video and share it if you like the video. And there is a link in the description for donating to our channel. If you like the videos, you can donate to our channel as well. Thank you very much.